Hello everyone, in this lecture we're going to be talking about some introduction of equilibrium reactions. So another way of saying we're just going to be talking about basic terminology of equilibrium reactions and what you really need to know about them. So technically the equilibrium reactions are going to be a two-way street, which means you can have the traffic going both ways, or another way of saying when you run into an equilibrium reaction, you have your reactants and products, and they're going to be preceding the reactions both ways. We have the reactants going to make the products, and at the same time we'll have some products going back to make the reactants. Now when we're writing the equilibrium reactions, and I can go and write a generic reaction where I have A plus B, and it's going to be in equilibrium. So when writing an equilibrium reaction, it's going to be a two arrows with half signs on both, and it's going to be pointed on both sides, and it's going to be making an AB. Now, some of the important facts you want to make sure you must know about the equilibrium reactions. Once the reaction has reached the equilibrium, the net concentration of your reactants and your products do not change unless you disturb those. Now, what does that really mean when we say disturb? So suppose if I change the temperature or if I change the pressure or I add some reactants or I add some products, that's when the disturbance means. Like in that particular case, your concentration of the reactants and products will change even at equilibrium, but as long as you don't disturb it, your net concentration of AB, like in this particular case, is gonna be the same as that of A plus B. And now, you may wonder that if their concentrations are not really changing, then the reaction probably not be happening at all, or the equilibrium will be a stay still equilibrium. But turns out it's going to be a dynamic equilibrium where you're still going to have some of the reactants making the products, and you're still going to have some of the products making the reactants back. Or another way of saying the rate of the forward reaction is actually going to be equal to the rate of reverse reaction. Suppose I have 5 moles of A and 5 moles of B, in that case going on to make 10 moles, uh, not 10, but rather 5 moles of AB, then what's really going to happen in terms of keeping everything at equilibrium? You will have another set of 5 moles of AB actually turning back to 5 moles of A and 5 moles of B. So that's what your dynamic equilibrium means. It's like saying, take an example of an airport. You have people walking into the airport and you have people walking outside the airport. So the net people that stays inside the airport doesn't really change. As soon as you have, let's say, 100 people walking in the airport, you will have those same 100 people kind of boarding out on the airplane and going out of the airport. So that's the same story here. If you make some set of reactants, then another reactants will react back to make that product so that your equilibrium is still intact. And then another misconception always students have is when you are at equilibrium, the concentration of your reactants and your products is actually going to be same. No, that's not necessarily have to be true. If it is the same, it's just a coincidence. But I would say 99% of the time they're not the same. The typical question they would ask you is the concentration of reactants is always equal to the concentration of products at equilibrium, and that's false. And we'll talk about how you're going to be determining the relative ratios of your concentration of the products and the concentration of reactants in a separate video. But I just want to touch base the equilibrium in this particular set here. So suppose I have a reaction where I react H2 gas with I2 gas, and then it's going to set up an equilibrium eventually um, to make an HI. So that's going to be your product. Let's say in the beginning or initially, I add the H2 and I2. So we don't really have an HI made. So when you're adding the H2 and I2, what's going to happen? The rate of forward reaction is actually going to be greater than the rate of reverse reaction. because you don't really have too much of HI made yet. But as the time progresses, you have more HI. As the time passes by, the rate of forward reaction is going to decrease and the rate of reverse reaction is going to increase. So that's very important to understand. So if I go ahead and make a graph out of it, suppose, so let's say I got the y-axis and I got the x-axis. So on the y-axis, I'm going to have concentration, and on the x-axis is just going to be the time. And then suppose initially I'm going to change the colors there. So I got this is going to be my H2 right there concentration, and suppose this is going to be my I2 concentration. And obviously in the beginning you don't really have any HI made, so that's going to be way on the bottom here. And then what's going to happen over time, your H2 concentration is going to decrease and I2 concentration is going to decrease because they're going to start making the HI. So I would see something like this. So let's suppose I get, so that's for the H2, and you can see something very similar for the I2 because they are 1-to-1 mole ratios. So I can have a very similar scenario for the I2 here. So let me draw the curve here if I could. Okay, and then for the HI, obviously your concentration is going to increase, and at a given time it's going to level out. So this is how it's going to look like. So this is where your initial phases were up to, I would say, if I have to draw a line there, I would say up to this point right there, you may not have your, let me see, up to this point, you don't have your concentrations or you don't have your rate of forward reaction equaling the rate of forward reverse reaction. So then after this point, or let's say this box right there, your concentration of HI is not changing, the concentration of H2 is not changing, and the concentration of I2 is not changing. And as a result, they set up so-called a dynamic equilibrium at this point. So this is when you have the rate of forward reaction equal the rate of reverse reaction. So initially you have the rate of forward reaction was high and the rate of reverse reaction was low, but as the time passes by, the rate of forward reaction decreased and the rate of reverse reaction increased until they become equal to one another. And when they become equal to one another, you ran into so-called a dynamic equilibrium. Hopefully this was helpful. If you have any questions, feel free to leave any comments in the section below.